Thank you for coming to the forum. The forum is about to begin. Please take a seat. Good afternoon, ladies and gentlemen. Welcome to Meet the Short Laureates, the challenges and the joy of doing science forum. The forum is about to begin. Please be seated. Today, the Leisure and Cultural Services Departments and the Shaw Prize Foundations have the pleasure to present this event at the Hong Kong Science Museum. Before the forum starts, we would like to invite the Shaw Laureates 2017, members of the Shaw Prize Council, the representatives of Leisure and Cultural Services Department, and the forum moderators to take a few photos. May I invite our guests to come onto the stage. Professor Ronald Well, Shaw Laureate in Life Science and Medicine 2017. Professor János Kollár, Shaw Laureate in Mathematical Sciences 2017. Professor Simon White, Shaw Laureate in Astronomy 2017. Professor Claire Vazan, Shaw Laureate in Mathematical Sciences 2017. Mr. Shing Wai Chen, Assistant Director, Leisure and Cultural Services Department. Professor Kenneth Young, Member of the Shaw Prize Council. Professor Y.E. Chen, Member of the Shaw Prize Council. Professor Tom Wen, Professor of Mathematics, the Chinese University of Hong Kong. Professor Meng Zhongzhu, Professor of Physics, the Chinese University of Hong Kong. Ms. Karen Sid, Museum Director, Hong Kong Science Museum. Thank you very much. Please be seated. It is our honor to have Professor Kenneth Young to give us an introduction on the Shaw Prize. May I invite Professor Young, please?
Good afternoon, ladies and gentlemen. Thank you for coming to this public forum organized by the Leisure and Cultural Services Department, the Science Museum, in collaboration with the Shaw Prize Council, in order to provide an opportunity for members of the public to meet, to listen to, and to interact with the Shaw Laureates 2017. The Shaw Prize was established in the year 2002 to promote and foster scientific research worldwide. It is an international award dedicated to honoring individuals, regardless of race, nationality, gender, and religious belief, who have achieved significant breakthroughs in academic and scientific research or applications, and whose work has resulted in a positive and profound impact on mankind. Since 2004, the prize has been awarded annually for distinguished and significant achievements in the following three scientific disciplines: astronomy, life science and medicine, and mathematical sciences. Each prize consists of a medal, a certificate, and a monetary award of $1.2 million. This is the 14th year in which the prize is awarded. The 2017 prizes were awarded just 2 days ago, with the chief executive officiating. We are pleased and grateful that the laureates, in addition to lectures at 3 universities yesterday, are here today for this forum. I leave it for the moderators to introduce the laureates. I just want to say at the very outset how impressed I have been by their total dedication over decades in working on problems of importance to humanity. Important not only for the impact on our lives and our health, but also important as part of the rigorous and relentless search for truth and understanding that distinguishes us from other species and define us as humans. While the Shaw Prize celebrates great achievements of the recent past, it is also intended to promote similar, dare I say, even greater efforts and achievements in the future. The science of tomorrow belongs to young people, and we are very pleased to see so many future scientists here today. I'm sure you will all be captivated, as I certainly shall be. Thank you.
Thank you, Professor Yang. Now, let us begin with the sections on astronomy. Today, we are much honored to have Professor Ming-Chung Zhu to be our moderator. May I invite Professor Zhu, please?
Good afternoon. It's my great honor and pleasure to introduce the Shaw Laureate in Astronomy 2017, Professor Simon White. I see many young audience. I don't know how many of you have had the experience of watching the stars in a dark and clear night. It's getting more and more difficult in Hong Kong now. I myself have been doing it since 40 years ago when I was in junior high school. And I still remember that whenever I looked at the skies and the Milky Way and so on, I would be wondering, how would the universe evolve to be like this? This must be one of the greatest questions in science. And Professor Simon White has done seminal work to providing a framework of the answer for us, how structures evolved in our universe. More importantly, he has shown by doing his research, he's shown by example, that we could study these very important, very fundamental questions with the help of powerful computer. So now we can actually simulate the evolution of the universe. We can change the physics, we can change the particles, we can change many things. We make our own universe. It makes it almost like a lot of fun that you can play around with the universe. So now these sort of simulations, sometimes you call them n-body simulations, become a very standard and powerful tools in cosmology. Professor White has also done a very beautiful and surprising work. He showed us that such simulations can tell us not just about the macroscopic universe, but even about some properties of elementary particles. It turns out that neutrinos, which is very abundant, and we now know that they have some finite non-zero mass. Turns out that neutrinos have a great impact on how structures evolve. And because of this sensitivity, Professor White could produce a very tight band on the neutrino mass, much tighter than what people can measure in the lab. So by studying the universe, we know something about the tiniest particles that drive our universe. So this is just an example of the beautiful work Professor White has done. So it's my great honor to invite Professor White to give his talk.
Good afternoon, everybody. It's a great pleasure to be here. So I started thinking about problems in astronomy and doing astronomy about 40 years ago, which is a very long time for most of the people in this audience. At that time, this was the biggest telescope in the world. It has a main mirror 5 meters across, and it sits on a mountain called Mount Palomar, south of Los Angeles. At that time, in the mid-1970s, it was already 20 years old. And even today, 40 years later, it still does forefront science. So this main instrument has lasted 60 years. Now, at the same time, I was using computers for my research, and this was the biggest computer I had access to. It was made by IBM. It was called an IBM 370, and there was one in Cambridge University. It was 2 years old when I started using it, and it was scrapped and thrown away 2 years later. Computers change much faster than telescopes. And in fact, since I started, computers have become 1 billion times more powerful than they were. And they can handle 1 billion times larger memory. They have 1 billion times more information. So this is a huge expansion compared to most other capabilities in our science. When I started, we programmed computers using punch cards, and you had to sit down and type on these little machines, and they punched the instructions on cards, and then eventually you'd get a whole deck of cards. You'd have to, the deck of cards would be in a big box, and in my case, didn't even have somewhere to read it in the department where I was working, so I had to take the box of cards, put it in the basket of my bicycle, cycle through the rain across the road to where there was a reader which you could put them in, and it would read the cards in, do the computation, and eventually you get the output back, and you get it in the form of print on a large stack of paper. It was a printer called a line printer, which printed 130 characters or so at a time, and we go, and eventually you get the printout. And that was all you got. There was no graphic printers, no way to make a picture. So that was a problem. The problem I was interested in goes back even further. So this is a picture of a cluster of galaxies, and all the white, light-colored blobs that you see here, these are elliptical galaxies. You can see there are many of them in this region. It's what's called a galaxy cluster. And by measuring the size of this region and how fast these galaxies are moving, you can estimate how much total mass, how much material is in this region. And this was first done in the 1930s by this man. This is much later in life. He was a Swiss astronomer called Fritz Zwicky. He did this calculation, and he got a strange answer. He found that the total amount of material in this region seemed to be more than 100 times the mass of all the stars. So apparently, most of the material in here is in some form we can't see. And this became known as the dark matter problem. And then that sat there for more than 50 years without a solution. Some people thought the problem was actually the laws of gravity were different for these big systems, or there's just a lot of stuff we can't see. So this interested me when I was a student, and I wanted to calculate what would happen if this extra matter was somehow attached to these galaxies just in the outsides and it wasn't shining. So to answer that question, I needed to ask, how would the system change with time? How would it evolve if this were the case? And there are about a few hundred galaxies in here, so I tried to calculate this. And luckily, this man, who is a Norwegian astronomer who was working where I was working, had all written a code which could calculate how stars would move inside a star cluster under the influence of their own mutual gravity. So I just took his code and reprogrammed it to follow what would happen with galaxies inside a galaxy cluster. And here they are distributed uniformly and expanding with the universe at this time. And I just asked what would happen as this system evolved. And a bit later, it got about 5 times bigger. So this bar is actually the same physical size here, and the whole system's expanded. And you see it broke up into lots of lumps. And then a bit later, these lumps coalesced into 2 big lumps. And then finally, it all fell into one single lump. So apparently, the way the structure evolved was starting smooth and getting gradually more and more lumpy until you end up with a single system. So there's several things to think about here. I didn't know what was going to happen when I started this calculation. So in some sense, this is an experiment. But it's clearly not an experiment on the real universe. It's an experiment on this set of mathematical equations, which just enforces Newton's law of gravity between all these particles. And so I couldn't calculate directly on a piece of paper how this would happen, but the computer did it for me. So it's a kind of computer experiment on the mathematical model. So then an interesting question is, does this have any correspondence with reality? And I was quite lucky that a couple of years later, this X-ray telescope flew. It was the first, it's on a satellite, and it was the first telescope which could take pictures of the sky at X-ray wavelengths. It took pictures of galaxy clusters, and it found some that looked like this, some that looked like this, and some that looked like this. So then it's very tempting to say, well, this is just kind of an evolutionary sequence. This is the early stage, this is an intermediate stage, then eventually it all collapses. So maybe somehow doing the computer experiment is helping us understand something about how the complex systems might evolve in the real universe. So that was 1976. So you can ask 30 years later, what happens if we try and do the same experiment? So as I told you, computer power has been increasing dramatically. So now instead of having just a few hundred at points in the simulation, we have 100 million. And we have to calculate the forces they all have on each other. You'll see with time it starts out very smooth, and as time gradually changes, small lumps form, and you start to see a pattern emerging with small clumps. And then you can see these clumps. It looks as though it's rotating, but you have to imagine that the observer is just flying around the system. This is to help you see the three-dimensional structure of the object. It's not really rotating. And you can see now a really complicated structure has emerged. And all this structure is eventually going to fall together to make one single system, which is supposed to represent the dark matter part of a galaxy like our own Milky Way. You can see now there are many, many lumps here, and these ones in the central region will start to coalesce, and you'll see a little later how a single system starts to emerge. So you look at this, it would be very hard to try and predict all this complexity just from the equations. You need the computer to try and understand how the interaction between all these different equations, all these different bodies, all these different lumps, how this nonlinear pattern evolves. And so this is, in a sense, is what we mean by a computer experiment. And what I find fascinating is you look at this kind of thing, you don't really know when you start what it's going to look like. And you can see here, actually, the person who made this movie made some parts green and some parts blue just to make it even prettier, but that doesn't really have any significance. But now you can see we're getting close time. There's a clear center to this system. There's a clear drop-off in the density of dark matter as you go away, and there are all these other bits of stuff flying around. So you get a very complicated structure. So the difference between this calculation and the first one I showed you is just 30 years of computing. Treat a much more bigger system, so you see much more complexity. But the basic conclusion is the same. You start smooth, you get lumps, and the lumps coalesce to make larger and more coherent structures. So for the next part, which I want to talk about the evolution of the universe as a whole, I want to show you this picture. So this is a modern picture. It's a picture of the sky taken by a European satellite called Planck. It's taken in light with a wavelength of 1 millimeter. So that's about the same wavelength as the microwaves in a microwave oven. And what you're seeing here is what's called the cosmic microwave background. And this is a map of the whole sky. And you can see there's a kind of pattern here. What you're seeing, I think, makes this one of the most remarkable pictures in all of science, because this is a direct image of our universe as a whole when it was only 400,000 years old. So today, it's 13.7 billion years old. But at the time we see, it was 400,000 years old. And in fact, this map is very nearly smooth. The intensity here is measured by a temperature, and the average temperature here is 2.7 degrees above absolute zero. And the difference between the red points and the blue points, between the peaks and the troughs, is only about 1 part in 10,000. So it's very nearly uniform, and just very small regions which are higher and lower. So back in 1980, when I was first thinking about this problem, the map at that time looked like this. We couldn't measure the differences, but we did know it was very smooth. And so the question is, it was very smooth when it was 400,000 years old, and it's very lumpy today. How do we make the transition? And it became clear from relatively simple arguments that if the whole universe was this smooth and nothing was lumpier than what than the limits you could see, there wasn't enough time to make anything. The universe would still be smooth today, which obviously it's not. So the hypothesis was we needed something back then, when the universe was very young, which was smooth and didn't interact with the light and the ordinary matter, because then it could be lumpy and you wouldn't see it in the light. So we need dark matter even then. So the question is, what could this stuff be if it doesn't interact with light? So one possibility, in fact the only possibility which we know to exist, is that it could be a neutrino, which interact very weakly with ordinary light, and those neutrinos had mass. And at the time, no one knew whether neutrinos had mass or not. So we tried to say, if neutrinos had mass, let's do an experiment and ask what would the universe look like. And when we did this, we found that the galaxy distributions should look like these pictures, whereas this is the galaxy distribution measured on the sky in the real universe. And you can see the structure doesn't correspond. The lumps here are much bigger, and the empty spaces are much bigger. So even though this is a computer experiment, we could exclude the possibility that that the dark matter was any known kind of matter, because neutrinos were the only possibility, and they didn't work. So it had to be something new. And then we showed if you took a new kind of matter, you could get it to work. You can see these look much more similar. And even if you look in the third dimension, we're now at the center, and this is looking away from us in distance. This is a slice of the real universe. These are slices of the simulations. You can see qualitatively they're similar. So this was the beginning of what's known as the cold dark matter universe. And this was me at the time. See, my hair is darker and shorter. These are my colleagues. So you can ask, that's what happens with 30 years of computers. This is what happens with 30 years for people. So you can see they dress better, their hair is shorter, but it's grayer. But that's the way life goes. Computers nowadays look like this. This is another younger of my collaborators who's great at programming complicated equations and making them work on very big computers like this one. This is just one row. There are several rows of cabinets like this for this computer. And they allow you to do simulations for how the structure grows. So here now we're looking at the structure growth in a larger region of the universe, and you can see the material gradually falling together to make an object in the center. So what happens with time is the contrast grows, structures become there, and you make the individual objects. So you do this with a large number of particles, in this case 10 billion particles, so 10 to the 10 particles in this particular simulation to represent the distribution. You get a very complicated structure. You want to see it in detail, it's best to take a spaceship and fly through it. So this is now flying through this virtual universe inside the computer. And that has a big advantage that in a virtual universe you can fly very fast. So this is 10 to the 14, so that's 1,000,000 billion times the speed of light. So that's pretty fast. You cross the whole universe in about 3 minutes. And you can see you find a very complex structure. The disadvantage is this is the dark matter, and we can't see it. So you have to somehow model the part that we do see so you can make the transition from the dark matter to the light. And now, if you put a virtual observer inside the computer, you can look at the galaxy distributions. So these are distributions of galaxies, so that we're at the center in each of these plots, and this is a distribution of galaxies in a slice of the universe. So these are real slices. These are slices inside the computer. And you can see, qualitatively, there's actually quite a close fit between the statistical properties in the two cases. And so by adjusting this, you can understand exactly what physical processes need to take place to get the match to be as exact as possible. So I think what you can see is this kind of work adds to the classical idea that we go to scientific truth by combining experiment or observation of the real world with a mathematical model for the processes which control things. And the problem is, for many processes, like the ones I've been showing you, but also like climate or economics, the systems are so complex that even though if the mathematical model is simple, we can't work out its consequences. And so the computer simulation allows you to do experimentation on the mathematical model, and then so to compare it with the observations. So we now have these three aspects which work together to try and improve our physical understanding. So I'm going to stop there.
Thank you very much, Professor White. Please take a seat here on the stage. The question and answer section is about to begin. May I also invite Professor Ju to take a seat on the stage to join the discussion.
So, Professor White, thank you for such a stimulating talk. The floor is now open for questions.
Thank you, Professor, for your very interesting talk. I'm a biology student, so sorry if it's a very naive question. I would like to ask about the Newtonian n-body problem. Whether each dot has its own mass, and if they interact, if they have its own mass, will it affect how the model will form? Thank you.
I'm not sure I understood your question. You're asking about the correspondence between the things that we put in the simulation and the real particles, or what are you asking?
All the dots are uniform, but are they the same, or each particle?
Yeah, in the simulations I've showed you. So, for example, in the movie which I showed you a fly-through to try and understand the structure, that followed 10 to the 10 individual particles, which are all of the same mass. But they're still much, much more massive by about 60 orders of magnitude than the individual elementary particles. So you have to think of them as just a random sampling, a Monte Carlo sampling of the true particles. And so, of course, an important question is whether this very coarse representation of the true distribution is good enough to get the structure right, and that you'll have to do careful testing through more numerical experimentation to see if that was enough particles. And the answer you find is it's enough particles for some things and not for others. So you have to be careful when you look at the results to understand which parts of the pattern that emerges are independent of the fact that we had 10 to the 10 and not 10 to the 20, and which parts that's important for.
Thank you very much for your explanation.
I guess you can do an experiment with the computer, which we can't do in the real world, which is to make the Big Bang happen again and again. So if you do that, what is the variation in the structure through the simulation? In other words, like how, you know, if you run the simulation from the beginning, there must be, you know, a great deal of
well, that's true. And so I showed you the picture where you were supposed to compare the blue points, which were the real world, with the red points, which were the observation. And you can see that the patterns were qualitatively similar, but the lumps were not in the same place. So the goal is to make the pattern be statistically equivalent, but not to actually simulate the particular realization of the initial conditions we have. So if you run another simulation with all the same assumptions and all you do is change the random number generator in the initial conditions, then you get something where the statistical properties of the distribution are the same, but all the lumps and the voids and the filaments are in different places. So that's the kind of variation you get. And that's fairly easy to control for, because in any case we're trying to do a very large region of space, so different regions of space are almost independent realizations of the process anyway. But there's a more complicated aspect to what we're doing, is although we think we understand the physics at a microscopic level, you know, it's like we understand microscopic physics and chemistry on the Earth's surface that doesn't allow us to predict the weather. And that's because we can't treat things in the detail needed for the macroscopic system. And so, particularly where to put the galaxies, we have the same problem. We can't treat the physics at that level of detail. So actually we do experiments where we change the representation of the physical process and run it again and see if it comes out looking better. So this allows us to do effectively numerical experimentation on the proper representation of the physical processes. Because we have to have some kind of coarse-grained representation of how stars form and how black holes explode and so on.
So for your simulation, you assume initial starting conditions which are relatively uniform. How do you account for the quantum irregularities that arose as a result of the great inflation and would thus have affected the distribution of matter in the early universe?
Yeah, that's a very good question, because of course if we set up our initial conditions and they were completely uniform, by symmetry they could stay completely uniform and we wouldn't get anything. So although the initial conditions are nearly uniform, the deviations from uniformity are very important. And so we make the deviations from uniformity be consistent with the pattern I showed you in the microwave background radiation, because there we can measure directly the pattern of structure in the universe when it was 400,000 years old, when it was very, very smooth. And so what we do is we take that pattern, or at least a theoretical representation of it, and we use that to set the deviations from uniformity at the beginning of our simulation. And that pattern itself is consistent with what's expected if all the structure arose in the very, very early universe in the inflationary epoch. So because you can also start from the microwave background radiation. So what I showed you, this picture, is actually the boundary of the whole visible universe, because the universe in front of this cloud surface is transparent, so we can see it, but it's opaque, so we can't see anything, at least the electromagnetic radiation that's behind it, so at an earlier time. But we can try and infer what could have happened at an earlier time to produce this pattern, and the simplest models for quantum fluctuations in the very early universe produce a pattern which statistically are consistent with what's seen. So this, you can take this microwave background pattern both as the starting condition for what I do, which is what happens in the late universe, but also as a way to test these theories of what happened in the very early universe.
Okay, the next question comes from the floor. So in case you're too shy, you're welcome to write on a piece of paper. Either English or Chinese will be fine. I will translate it for you. So I'll simplify this question. Basically, it is about the neutrinos. Is it the gravity of the neutrinos that affects the structures? How can such a low mass particle change the structures of the universe?
That's a very good question. So you can ask, why can we say that neutrinos are no good for the dark matter, but some other hypothetical particle called dark matter is great? And that comes from this question about what it predicts to come out of the early universe, so what it predicts for the initial conditions. And it turns out that the neutrinos interact weakly with ordinary matter in earthbound experiments, but the interaction is not zero. And in the very early universe, the neutrinos were actually in interaction in equilibrium with all the other particles. And so that allows us to calculate when everything was nearly smooth, and we can calculate rigorously, formally by what's called using linear theory, it's possible to calculate in a simple way how the structure evolves. And it turns out that the structure in the neutrino distribution is smooth on very small scales. So the initial conditions in a neutrino universe are smooth on small scales, but still have structure on large scales. So that's why in the picture, when we evolved it, you found you got big lumps and no small structures. So the difference with the cold dark matter is the interactions were even weaker in the early universe, and the particles were more massive, and this means they had not only the big structure, but also smaller structures. And it's the smaller structures which you saw in the movies, making little things which gradually fell together to make bigger and bigger objects. And so that's the difference. It's the different kinds of particles give rise to different initial conditions in the early universe, and then we just put the conditions into our calculations and see what happens. And so in a sense, all these particles interact very, very weakly with light and with ordinary matter, but they interact in different ways, and those interactions actually do make a difference to what comes out of the Big Bang.
Thank you for your lecture. I have a question. How do you account for universe expansion during your simulation?
Well, we put it in. So it's initial condition. We start everything, you can think of it, we start all the material flying apart, and it just continues to do so. So in a sense, it's there as the way we set the calculation up.
Oh, I actually still have another question. We have an infinite universe, but when you put it in simulation, you have to consider a bounded physical system. then how do you get rid of the boundary effect?
That's a very good question. Although, on the first point, we don't actually know that we have an infinite universe, right? What we can see is definitely a finite universe, because all we can see is as far as this last scattering surface, and there's definitely a finite volume inside that. And the overall, whether the universe as a whole has finite volume, depends on its geometry and even larger scales. And we have some limits on that, but basically we don't know. So it could be infinite, and it could be finite. So this is an unresolved question. But in any case, it's much, much bigger than the simulations I'm showing you. See, our question's still a good one. And what we do in the simulations is we take a cubic region, and then we identify the top and the bottom and the left and the right and the front and the back and make it periodic. So what happens then, it's effectively infinite, but it's periodic. And that allows us to not to avoid having any sharp edges.
Thank you for your answer.
Another question in the back?
Is there any special methods used in calculating such a complex structures to show to us the evolution of it? I think, as I know, if I use a console software in the computer, it will take a lot of partial differential equations, and I will break down my computer.
Well, the whole point was the computers are getting bigger, but conceptually, I show you a simulation with 10 to the 10 particles. All that it did was, in effect, was to evaluate the Newtonian force, so G m1 m2 over r squared for every pair of particles. The complication, of course, is you have 10 to the 10 particles, you have 10 to the 20 pairs, so it's a lot of operations, so you have to find ways to speed things up. But conceptually, it's not complex. The complexity comes, if you like, from the initial conditions and the nonlinear development of the initial conditions, which leads to this geometric complexity. And that's a property, in a sense, of the initial conditions, which in one sense are very simple. They're the simplest possible stochastic initial condition, what's known as a Gaussian random field. But nevertheless, that evolves into a very complex structure.
Yes, but I still have a question. I want to know, how do you simplify the interaction between the particles or the matters? No simplification?
No. The algorithm has to find ways to speed things up. But conceptually, what we're doing is really evaluating the forces between all pairs of particles and then just integrating the equations of motion.
Okay, if not, let me read the following question. How were you able to observe the dark matter when it cannot be seen with naked eyes? Also, how does the mass affect the expansion of the universe, and how can you simulate that?
Well, it turns out the dark matter only interacts with ordinary matter and light gravitationally. So that means if you see it, you have to see it by its gravitational effects. So an example which you might well be familiar with is you can tell if you see a star which is just going round and round in circles, and there's nothing in the middle, that suggests there's a black hole in the middle. Right? So you can't see the black hole, but you can see the other star going around it. So what you're using is the gravitational effect of the black hole to see the star. So if there's a large lump of dark matter, that acts gravitationally on everything, in particular on the galaxies you can see. And so that's why Fritz Zwicky could tell there was dark matter in the Coma cluster, because he saw the galaxies were moving too fast. If you just took the gravity of the things you can see, they should be going slower. There's a way to be more precise about this, which is if you have a lump of dark matter here, and you look at a galaxy which is behind it, then as the light comes from the distant galaxy to you, it has to go through the cluster. And as it does that, the gravitational effect of the cluster bends the light rays, and that distorts the image. So it's like you look through a lens, and it's not a very good lens. Everything you see looks distorted. So we can see that effect. We can see the distortion of the galaxies in the background. By measuring how much their images have been distorted, we can work how much mass there has to be in the cluster. So this actually allows you to measure the mass distribution in the cluster by its effect on the light of distant things coming through it.
Is this an example of entropy when the universe went from order to disorder?
That's a very difficult question. the highest entropy system is thought to be one in thermal equilibrium. So that would be everything at the same temperature and uniform. And what I've been showing is you start with something which is uniform and hot and becomes cold and structured. So this does not look like entropy is increasing. It looks like things are becoming more. So it looks like entropy is decreasing. And this is it's actually a very deep question because it depends on how you assign entropy to the gravitational field itself, which is an unsolved question. So another example is if you take a cloud of gas, it can be relatively cool, but it can hold itself together if it's massive enough by its own gravity. What happens with time is it loses radiation, so it loses energy. What happens is then contracts, becomes more compact, and gets hotter. So the result of losing the energy, which you'd think would normally cause things to cool down, actually makes them get hotter. So a gravitational system like a star seems to have a negative specific heat. You take energy out and it gets hotter. And that's another effect of the gravitation. And so these kinds of effects make it very difficult to define exactly what you mean by entropy when you're dealing with gravitating systems.
Another question here. What is the uncertainty of the model?
Well, there are two aspects to the uncertainty. One is, there's a mathematical model, and the computer calculates the solution for a set of initial conditions. So in that sense, the experiment is a mathematical experiment. You're asking, have you got the right solution for this particular problem with this set of equations and these initial conditions? So then that's easy to handle because you can do tests and work out whether the computer has got a solution which is good enough. It's never going to be accurate in the sense a mathematician would like it to be accurate, but it can be close enough to make inferences about the structure. So that's relatively easy to do. You can test it by running the simulation with different integrators and so on. The more difficult question is, of course, the model that you put in is only an approximation to reality. And so that part, all our physical models are only some approximation to reality. And there, actually, the most important thing is when the model fails. Because when you're sure you've solved the equations correctly, and the answer still doesn't agree with what you observe, this means that the your mathematical representation of the physics is wrong, and you have to change it. So that's actually where we learn about the astrophysical part of the problem.
Okay, there's a question on this side.
Good afternoon, Professor. I would like to ask a question. There's a famous paragraph in the world that means that in the unseen galaxies, there is no aliens because if there is any aliens live in other corners of the galaxies, they can seal in any corner to the Earth in this maybe 4.6 billion years. Do you think is there any aliens live in the world or live in the galaxies or in other corners? Do you think so? Sorry.
I don't know. But I think one of the developments in astronomy in the last 20 years is we've come to understand that most stars, like the Sun, have planets, and very frequently they have planets which are like the Earth and have environments which are like that on Earth. So the kind of environment we have on our Earth happens millions or even billions of other places in our galaxy. So, and a lot of those systems are older than 4.6 billion years. So many of them have had more time to think about evolving life than has happened on Earth. So it would need something very special that we don't understand about the conditions on Earth for this to be the only place that's made life. On the other hand, the nearest planet that's made life could easily be much further than, say, 100 light years away, because compared to the size of our galaxy, 100 light years is not a very big region. So, if it's 100 light years away, then they won't know we're here yet, because basically we only became visible to the aliens once we switched on TV. And we started broadcasting TV. The radio waves are loud enough that, any civilization which had a telescope as good as ours would know if it was within 70 or 80 light years of the Earth. Maybe they have, but it would take them more time to get back, so they haven't had time to come and visit us yet. But, you know, I don't think there's any sign they've been here so far.
Well, actually, I always suspect that some of my students are aliens, so I think they are here already. It's a question from...
It's time.
Yeah, this one first.
What does your model show about like the implications on the fate of the universe?
Sorry, about what?
The fate of the universe.
The fate?
Yeah.
I don't think this is really related to my model. My model follows the detailed evolution, so we could extrapolate further, of course. We don't have to stop the computers today. It would get very time-consuming. But I think we don't know. What we do know is that currently the expansion of our region of the universe is accelerating. So if that continues, then it'll get very cold and very uninteresting place in about roughly 100 billion years' time. All the stars will have died out, and most activity will cease, so it'll start to get really cold. And you know, maybe things will never come back together. But on the other hand, outside the microwave background surface, it's possible that conditions change. And so we don't really know. That's an extrapolation. It seems that the things we can't see look the same as the things we can. And this may or may not be the case.
Then there's a question in the back.
Good afternoon, Professor. I'm a student from CUHK Shenzhen. And I want to ask that in your analysis of the simulation results, what method do you use? You know that it's very unlikely that only for the physicists to analyze those numerical results. Is it helpful for you to use that machine learning stuff or that something like that?
Well, it's true that you get very complicated patterns out of the simulations, and now the surveys of the universe have millions or tens of millions or even hundreds of millions of galaxies, so they have also very complicated structures. So it's possible that machine learning or some automatic routine would help find patterns that you don't see by other techniques. But at the moment, this hasn't played a very large role. There are many techniques which allow you to analyze the structure in a more directed way than just telling the computer to look at it and see what it thinks.
The time is almost up, so let me take the opportunity to ask the last question. So it's really the very simple-minded questions compared to the questions before. So what advice would you give to the young students in the audience aspiring to be cosmologists, scientists?
I think you should do what you find interesting and what you think you're good at, and you should worry about whether this is going to lead to a job later.
Okay, thank you. That's a good way to start.
Thank you very much. Please return to your seats on the floor. Now, we come to the sections on mathematical sciences. It is our honor to have Professor Tom Wan to be our moderator. May I invite Professor Wan, please?
It is my honor to be invited to moderate this section. Okay, I'm going to introduce to you Professor Kola and Professor Wilson for their short prize in mathematical science 2017 is for their remarkable result in many central areas of algebraic geometry, which has transformed the field and led to the solution of long-standing problems that had appeared out of reach. Okay, so my job is to explain to you what algebraic geometry is and their job. But this is really a challenge. Okay, to explain it, the term algebraic geometry in layman term, naively, you may think of your high school algebra and high school geometry and put them together. Of course, this is too trivial, and it certainly won't reflect the significant contribution of both professors. Okay, and but in a way, this is really a study of the geometric and the algebraic structure of some geometric object divided by equations. so-called algebraic equations for you. And it's because of this, it's in the middle of the common area of several major fields of mathematics, such as number theory, geometric analysis, and so on, complex geometry, and all that. And even in modern day, high energy physics, which is the famous string theory, okay? And so this is a hard job for me, so therefore I will let the Laureate to tell you more about the subject. So let me first invite Professor Cora of Princeton University.
So, thank you very much. It's a great honor to be here. And so I will try to illustrate a little bit how you can take high school algebra and high school geometry together. And if you do the mixing in the right way, then you get a sharp prize after a while. And so I would like to talk about some algebraic surfaces. And so, well, so I would like to start with some examples of surfaces. But surfaces are everywhere. So, you know, if you are sitting on a chair, then you're sitting on the surface of the chair. If you're walking somewhere, you're walking on a surface. And yesterday, in my lecture at the Chinese University, I talked about some complicated surfaces that have interesting grids made up of lines and circles. Today, I would like to show you some examples of some interesting surfaces that are made up of interesting grids on them. And yeah, so let's start with the first example, which is an airport tower in Kobe. And one reason I really like it, because you see, first of all, you see the circles. So the surface is made up of these circles. And there are two sets of lines. It's sort of a little harder to see, but there are some lines that sort of go to the right and some lines that go to the left. And so, well, the surface is an example of what's called a one-sheeted hyperboloid. And I just found out a few weeks ago, through digging through some old journals, that actually the first person who might have discovered that the one-sheeted hyperboloid, it has two sets of lines. It was Sir Christopher Wren, who then went on to design St. Paul's Cathedral in London. So it is very nice that this example now exists in architecture. Well, I hope that many of you actually have seen this in real life. This is the Canton Tower, which again, the surface is a hyperboloid, but here the architects decided to have an interesting twist, that they have the left-going set of lines, but they did not add the right-going set of lines. Instead, they added some interesting spirals to it. And so that again, they started with the same mathematical structure that was before, but made it architecturally more interesting. But this is a local example. I think it is the facade of the art museum. So here you can see that this is made up of some vertical lines, and then the horizontal curves, they are ellipses. Except again, the architects made a little twist that here on the right, instead of this ellipse going back this way, they added a little tail to it. So they sort of start basically the mathematical structure, but then they make it something more interesting, more pleasing to the eye. Then this is a museum in Shanghai. So from my point of view, this may not be a really good example because it has lots of flat surfaces. So left side is very flat, the right side is very flat, but where the two flat surfaces meet, instead of just creating an edge, they create these very nice looking grids which look more or less like hyperbolas that connect the two surfaces together. Then another old example, I think it's a 10,000 life vase that again is, I believe, here in the Art Museum in Hong Kong, and then here the artist arranged, I believe, 10,000 characters, meaning long life, along this grid. So again, there are the circles that go around, and there are some more complicated curves that go along the edge. This is probably more or less a degree 3 algebraic curve, so it's more complicated, but this is a nice example of artistic illustration. Again, that if you create an interesting grid, you can get some very nice pictures out of this. And then, well, with 10,000 long lives, maybe you can actually live longer than the universe. We don't know that. Okay. Now, well, this is, well, the first approximation. This looks like an armadillo, but in fact, it's a the Science Center in Glasgow. Again, you see here that there are these vertical-looking elliptic lines, and it's harder to see, but there are these horizontal line structures. They again look like ellipses. Now, then this is the Viceroy Hotel in Abu Dhabi, where again you can see two nice sets of ellipses that create the roof. This is again an example I hope that many of you have seen, is the National Theater in Beijing, and especially on the right-hand side, you can really see both the horizontal and the vertical ellipses that go completely around the building. Start at the front and they end up then at the back. And then this is a somewhat more interesting example from my point of view. It is the new roof of King's Cross Station in London. If you just look at the lower part, then it looked like two sets of hyperbolas, but then in the upper part, where they introduce a third set of hyperbolas. So the lower hyperbolas continue going left, going right, but then a new set of hyperbolas comes in. Okay? And so these were just some architectural examples of some surfaces that you can assemble, so some grids of relatively simple curves. Now, my main interest as an algebraic geometer is to understand more complicated surfaces. And so I like to look at the high school algebra part, that write down an equation. And on the other hand, I would like to understand what kind of geometric object do I get out of these equations. And so my main interest is understanding sort of all possible surfaces, not just the ones that are simple to draw, but everything possible. And especially trying to understand then how these surfaces, they can develop with time. I think I'm more interested in sort of short time development, not long time like Professor White. And so now, next I will show you some especially nice examples. And so you should think about this like if you like to watch birds, then when you start, you are interested in the especially colorful ones. And then when you become an expert, then you might become very much interested in some little bird, which is just brown, but it's rare in your area. But so the first approximation, at the first step, you are probably looking at some birds that are very blue or very red or yellow. Now, these pictures were created by Professor Herwig Hauser in Vienna. He can do what I think a really spectacular job. So let me just show you some of his examples. So each case, I don't know, can you see the equation? It's at the lower end, and then there is a surface. And so the color is just added to it. So what the equation tells us is only the shape. The color is only put there so that you can see it better. Here's another example. Well, here is the next one. And you see what I especially like about it, that there's some very simple equations, just a few monomials, and you add them together, and you get these really amazing looking shapes. Okay? Well, if 4 people want to drink at the same time, this is very convenient and handy. Then where there is two flowers together. This is nice blue. Again, the equations are very, very, very simple. Okay, so here maybe there are 3 parts of it. Okay, now the equations start getting a little more complicated, and you get this shape starts to look like a starship in some movies. And again, now here we start getting into more interesting coefficients. There's a 10,000 there. That is exactly 10,000. It doesn't matter, but it should be something reasonably large. Okay, here's another one. Okay, now then I would like to show you some equation that depends more on exactly how you choose the coefficients. That's a famous degree 6 surface discovered by Professor Barth. There is this unknown phi in it, which in fact you have to choose very carefully. There has to be precisely the golden ratio. And then if you do that, then you get this picture. So this is made up of lots and lots of pieces, but the pieces exactly touch each other. So those 2 cone parts, they touch. Okay. And now, finally, I would like to show you just a little bit what can be done with an equation. That if I look at an equation like this, then how do I start to actually analyze it? So then I look at this equation. And now, as you have seen, most of the surfaces we have at most parts are nice smooth, but there are some interesting parts where the surfaces, they self-intersect or they develop something like a cone. So these are the features that I would like to find. And now it turns out that for this I need to compute the partial derivatives, where there are 3 of them, and then I have to solve this system of equation. Now this can be rather complicated to solve such a system, but in this case it will be the x-axis and the z-axis. So something special will happen along the x-axis and the z-axis. And there are some 2 special points. Let me not say exactly how we see it at the origin and 0, 0, minus 3. Now, then another thing we can do, you can notice that if you write this equation like this, I just rearranged the terms a little bit. This looks like an ordinary degree 2 polynomial in Z. Now, if you want to solve a degree 2 polynomial, then in middle school or high school, you learn that you have to write down its discriminant, the quadratic formula. So then again, I did that, and it is the discriminant that tells you something interesting. So then you compute the discriminant, and you would like to figure out what it is. Now maybe at the end of high school, you learn that you can switch to polar coordinates and in fact solve this. And then, well, this is not that hard to graph, and you get this shape. So that means, so please remember that the x-axis and the z-axis where something interesting happened, and there is this shape. And now, well, if you think a little more, then you can get a movie going about this. I think someone else is supposed to get the movie going. Yes, and so this is the movie. The z-axis is vertical, the x-axis is the horizontal, and again, it looks like it's rotating, but in fact, we are flying around it just like, okay, now here is that shape, the cat's eye shape, the upside down cat's eye that we computed. That's the discriminant. There is a special point, 0, 0, minus 3/2. We just flew around it to see it. Again, you see that 2 part comes together. And then we fly around it again from the other side again, see what it is like. And then again, if you back, okay, it's a little slow, so we are at a low warp speed. Okay, well, you can see that along some axes, two branches of the surface meet here at the lower end, and now what's vertical now is like a paper is just folded. So these are the things. We are back at the original surface. Thank you.
Thank you very much, Professor Kolar. Please return to your seat on the floor. Now, I would like to invite Professor Bazan to deliver her presentation.
I decided not to give a general overview of my work. I don't think that would be very useful. I wanted to discuss a notion which is very important in geometry. I think there are two basic notions, which are the dimension and the degree, and I am going to discuss the degree. So we started saying that algebraic geometry is putting somehow algebra and geometry together, and the degree is something that we know very early when we learn what is a polynomial, and so it's the case where the degree is very easy to define. If you consider a polynomial, P, so it's a formal expression, combinations of powers x to the I of a formal variable x, and you consider only n such n plus one such term, and the degree is the highest power for which you have a non-zero coefficient appearing. So we have this easy notion of degree. And when we have several variables, and the polynomials, they are combinations of monomials. Each monomial is a product of powers of the variables, and you make a combination of them. And for each monomial, the degree will be the sum of the exponents. Okay? So for a general polynomial, we will so it will be a combination of all these monomials with a given coefficient, and the degree of P will be the maximal degree of a monomial effectively appearing in the polynomial, so that we have a non-zero coefficient in front of it. But so, of course, particularly interesting are for us in algebraic geometry the homogeneous polynomials, for which all the degrees of the monomials effectively appearing are the same. So we say homogeneous of degree D when it is a sum of combinations of monomials of a given degree. So sigma of I k is a given D. There is a process which may look very artificial. It's an algebraic process which is called homogenization, which allows to starting from any polynomial in several variables to make it homogeneous. And the trick is to add an extra variable x0 and to multiply each monomial which appearing, which might be of degree smaller than D, by the adequate power of x0 in order to get the degree D. So it's a formal operation. So what is formal is a priori not very interesting. What is nice is that this operation is we will see a sort of geometric version of it when I will explain what is a projective space compared to a fine space. It's a way of looking at what what happens at infinity. We have been discussing what means for space to be infinite, this notion of finiteness or infiniteness in mathematics, this is summarized into being compact or not compact. And mathematicians, for me at least, they definitely do not like non-compact things. So we like to see what happens when we go at infinity. And so for this, we want to add points at infinity. And projective geometry is an example of that. And the homogenization process, it's a sort of algebraic step to achieve this compactification. And you note that the original polynomial P, it is just recovered from the its homogeneous version by restricting to x0 equal 1. Okay, so we lost nothing in that process. Okay, so that was algebra. But now I am going to speak about something totally different, which is topology. And we said that we are going to put together algebra and geometry, but in fact we are also putting together algebra and topology. And it's something which is a priori very different, because in algebra, well, we will deal with polynomial functions, very highly regular functions. And in topology, we will consider a priori only continuous function. And a notion of major importance for the development of the topology, and I would say also for a foundation of modern mathematics, is the notion of the degree. So let me explain in a few words what it is. So you consider an open set inside the Euclidean space, R to the n, and you consider a continuous or maybe differentiable map with value in R to the n. The key word here is proper. Proper is the notion of compactness for a map. Proper, that means that when you consider a point in the image, you consider it's a pre-image, that is all points that are mapped to it. You don't want that they can go to infinite. So, for example, when your point u in V tends to a certain value in the open set V, then you consider all the points which are mapping to it, they are not going to infinity. So that's the notion of properness. So how are we going to define the degree of this map? It's a fundamental result, it's a theorem of Facade, which says that for such a map, most value of are regular, which means that if you consider any pre-image, any point mapping to U by this map, then the differential at this point will be an isomorphism. The differential is a linearization of the map, and that implies by the inversion theorem that the map is a local isomorphism between U and V. Okay. Now there is a crucial point to introduce here, the notion of orientation. So you have this linear map at each point in the pre-image. It is an isomorphism between the two tangent spaces. And a linear map, either it preserves the orientations or it inverses the orientation. So typically, the identity map, x1, x2 maps to x1, x2, it preserves the orientation, but the map which exchanges the two variables, x1 and x2 maps to x2, x1, this one changes the orientation. Okay. And the degree of the map F over the point is you count the pre-images, so by properness you have only finitely many of them if V is a regular value. And the point is that you are not counting them in a naive sense, you are counting them with a sign. And the sign will be positive if the map does not change orientation near, and it will be negative if the differential changes orientation at the point. And so that gives you a number, and the crucial, the main theorem of the theory is that this number, in fact, is independent of the choice of the regular value v, as long as your v is, so you need some essentially connectedness statement. Of course, you should be able to pass from any value to another one continuously. So you want the v to be made of only one piece. And then that means that you get out of this a number which does not depend, in fact, on the point we have. So here there is an example. So in fact, this curve that I have here, it's the same as the real line, and I consider as a map the map which projects to the vertical map, which projects the vertical projection, which projects to the x-axis. So you see that if I am here, I have as an inverse image only 1 point. Okay, so that gives me degree 1. If I am here, again, I have only 1 point. But what happened in between is I have 3 points, 3 values over each, for example, here, I have 1, 2, 3. And the point is that there is no contradiction. 2 of them have to be counted with positive sign and 1 with negative sign. And that's the reason why, finally, the degree is always 1 for all the values. So, okay, so this is now there is a tricky thing in that story that, in fact, this curve is more or less a graph of a cubic polynomial. So, in fact, what we are counting here is you have a polynomial of degree 3 in one real variable, and we are, for each value of x, you are counting the number of solutions to the equation p of y equal x. So, and it is painful that we started from a polynomial of degree 3, and we find that this map has degree 1. And the reason is that we are not over the complex numbers. So they are missing pre-image, which will appear if we were in the complex setting. If we were working over C, in this situation, we would get three roots for all values of the parameters. Okay, so So I wanted to say something about the space and the ambient space and how to make the space compact. This is our favorite space in algebraic geometry. It is a projective space, so it's a way to make compact the usual flat space. So here, the usual flat ambient space, it's this affine space here, z equal 1. As you can see, it parameterizes lines in the ambient space R3. But when the line goes to infinity, when the point goes to infinity, the line that you get becomes more and more horizontal. So basically, to construct a projective space, we add to this affine space R2 what is called the circle at infinity, parameterizing lines which are horizontal. So now projective manifolds, they are defined inside the complex projective space by homogeneous polynomial equations, homogeneous as I explained in the first beamer. And the degree of such a projective manifold can be defined in some sense as a topological degree. So it's here that I use the fact that I am working with a complex projective space. Suppose that your complex manifold has a dimension n. You choose a linear projection from your big CPN to a smaller CPN by the linear projection. It's just forgetting about the number of variables. there is you have to assume that the center of projections, where all these coordinates vanish, do not meet your x. And then you can define the degree as the degree, the topological degree of this projection. And in fact, here I assume that the variety is algebraic, but in fact, that definition works as well for, in general, for complex submanifolds of the complex projective space, which are more generally defined by holomorphic equations. And I wanted to explain a very important result by a famous Chinese mathematician, Zhou, slightly less famous than Chern, but for algebraic geometry he proved a very important result. And one of his famous results, which have been very much used and generalized, is the fact that if you consider a complex manifold in CPN, so a priori defined by holomorphic equation, it is in fact algebraic, that is defined by polynomials, that is homogeneous polynomials. And in fact, the same proof will show an even stronger result, that if you have any complex algebraic variety in projective space, or complex manifold, it's the same by the first result. If it is of degree d, it can be defined by polynomial equations of degree d. And that the proof is, well, it's explained here. I think it's too late to give the proof. So I stop. But I just wanted to add the two remarks. The properness was a crucial notion to define the degree, and this is the projective space here. It has been used to work with a compact ambient space, so that, for example, these projections they are proper because they are maps between the compact spaces. And the second point is why complex numbers work better than real numbers in that story. It is the fact that if you consider a holomorphic map like the one which we got by considering this linear projection restricted to a complex manifold, its differential at any point, it's C linear, and because of this, it preserves the orientation. And that means that in that setting, when I compute the degree, I do not have to make an alternate sum with a minus or plus signs according to the orientation. You get only plus signs. So the degree is just a naive degree of counting pre-images. So I'm going to stop now.
Thank you very much, Professor Facade. Please take a seat here on the stage. The question and answer section is about to begin. May I also invite Professor Collard and Professor Wen to be seated on the stage too.
Should I go through this question first or let the audience ask first? Okay. Any question from the audience? Huh? No? Okay. Oh, that's right. One over there.
Thank you for the very interesting talks. I would like to ask a question to Professor Collard. First, you mentioned that you approached the study of surfaces which move throughout time. And since I'm interested in the same field, maybe I would like to ask a suggestion for my research. How would you proceed to study the interaction of two surfaces which moves throughout time? And in particular, how do you handle the interpenetration of them, assuming that they cannot cross each other? Thank you.
And so I think this is indeed a very, very hard question. And so I think if I could stay here for a whole semester and give a lecture course, I could answer. But yeah, you are completely right. This is a very, very difficult question.
Thank you.
Okay. Second questions? In the middle.
And now my question is a lot more general because I'm a year 3 medical student from HKU. And I find all this mathematics very complicated, but at the same time, I'm sure that it has a lot of very important uses in the real world. And I just want to ask, like, not so much about the research, but how did you find yourself pursuing this particular topic of mathematics? Like, I imagine you didn't know from a very young age that you were going to study algebraic geometry one day. Like, what was the journey like that led you to being so interested in this particular topic? Thank you.
Of course, when you start in mathematics, you don't study first your research topic. So I followed many courses in other fields, like, for example, Riemannian geometry, differential geometry, complex analysis. And the reason I have been attracted to algebraic geometry, I think, is what I like very much in algebraic geometry is that maybe you are aware of the fact that in the 60s, algebraic geometry has been totally refounded by mainly by the Grothendieck school. Well, it was not only in France. After a while, also many people visited France, and finally so the fact is that within 10 years, this domain, which had existed for 200 years, which had started very much in the complex side in the 19th century, suddenly it was given an incredible theoretical body of definitions. The idea being that things should be funded rigorously. For example, here I explain things which may seem very bizarre. Namely, I started from polynomials, this is algebra, and then suddenly I did topology. And typically, algebraic geometers in the 60s, they wouldn't do that because they wanted to refund everything from inside algebraic geometry with, so for example, typically I use the usual, what is called the usual topology of the ambient space, and the modern algebraic geometry does not want to use that topology, so you create first the Zariski topology and then the étale topology. Okay, so to give examples that showing that this domain is extremely knowledgeable. So I liked the fact that there is such a beautiful theoretical body. But on the other hand, what is remarkable is the fact that there are many beautiful objects. Precisely what Collard showed is that you can. There are so many interesting shapes, and shapes for us there are several classes of varieties with very different, very distinct properties. And it's a little specific to algebraic geometry that we have both large, very beautiful theory and a large variety of interesting objects to study. So it's nice because first of all you feel clever when you learn the theory, but then you can also really attack using it on a specific object, your favorite class of market. So finally, to answer quickly your question, it's I liked many sorts of geometry, but this one I appreciated. I mean, for aesthetical or very really personal reason of a good balance between this general theory and practice, being faced to certain natural object or explicit object.
Thank you, Professor. How about you?
So I started algebraic geometry in the spring of 1979, when my algebra professor told me that nobody can understand algebraic geometry, that is too hard. And then I was young and I was proud, and I decided that I show him that there is someone who can understand algebraic geometry.
Thank you.
Great. Actually, this is almost the same question here, so I can skip this one. Okay. And from the audience again. Okay.
Here's a question for both the professors. So can you comment on the relationship between geometry or topology with physics? Do you believe that geometry provides the ultimate answer to our understanding of the universe?
So I believe the ultimate answer, if I remember right, is 40. Yeah, 42. Sorry. So the ultimate answer is 42. But and so for some reason that is actually a total mystery to me, and I think to many people, mathematics can be used to describe the universe very, very efficiently. And I really don't understand why this is the case, why this should be the case, that the purely logical part of mathematics can actually describe the universe very well. And so it is possible that the mathematics is the only thing we have, and maybe at some point someone will discover a completely different discipline that will match the universe much better. You know, the quantum world has a very complicated mathematical description, so maybe there is a simpler non-mathematical description, but it's maybe someone from the audience will find it.
Professor? I think there are two parts. I mean, if you believe that a certain model is meaningful physically, then we mathematicians we work with a mathematical model. So it's a way of not answering the question. We know that what we know is that our field can be useful to study certain mathematical models of the universe. Assuming that I know what is the universe. So in particular, we have been particularly concerned in the 90s since the 90s by the development of string theory, where they, for some reason, physicists concluded that the good vision of the universe with 4 dimensions, so 3 for the space and 1 for the time, will be, in fact, a 10-dimensional object, geometrically, made of the usual 4-dimensional one, cross a sort of a compact geometry, which is 6 real dimensional, but in fact 3 complex dimensional. And so there was this notion of Ricci flat, which in the complex setting became what we call, due to the work of Yao, Keller-Einstein metrics. And finally, the emphasis due to the work of these people, so I am not sure if it is really serious physics, but for us it was very nice, because suddenly the Calabi-Yau threefold became extremely fashionable, and we were encouraged studying this geometry. So there is a small problem that this geometry, there are many of them, and they have moduli, so they deform. So that I'm not sure that the universe is supposed to have so many parameters. But so it's to give an example that I cannot really answer your question, because it has a sort of a philosophical dimension. That is, I think the problem for everybody is the fact that even not mathematically, but that we can understand anything in the real life and in the universe, it's already extraordinary. What I want to say is that, well, once you have made this modelization, the example of string theory was one, then we really can do geometry, and then we can do serious things.
Thank you.
Okay, I think it's time for some question on my hand. I just received one very interesting one. I think everyone wants to know that. The question goes like this one. Right now, we use X, Y, Z to show 3 dimensions. Okay, so we can picture that for them. But is there any way we can visualize high dimensions, like 4, 5, 6 dimensions?
So I can only see 4 and 5, and I have to close my eyes to it. And
Me, I am happy with the high dimension.
Okay, what about the picture, the movie you just showed us? So.
And so I really cannot, maybe I can give some analogy here. So, for instance, if you look at a picture of someone, then there's a two-dimensional picture that you see, but you understand right away that it's a three-dimensional object. And so, for instance, if you look at the two-dimensional picture of someone, you have no problem understanding that there's a person there, and the person is three-dimensional. This does not bother you at all. And so I think sort of the same way, if I can see sort of two pictures of a four-dimensional object, then I can sort of see that there's a four-dimensional object, that someone took these two different pictures. So that this picture shows sort of this third dimension. The other picture helps me imagine the other third dimension. So out of these two, I can, especially if I close my eyes, I can sort of start to see something what happens in dimension 4. So I am reasonably good at imagining dimension 4. Or to some extent I can do, if I have 3 pictures, then I can get to dimension 5. So after that it becomes very unreliable. I can sometimes...
So maybe I wanted to add something. So for dimension 4, if you think that one dimension is time, it's very easy to understand it conceptually. And not only conceptually, of course, the notion of dimension is conceptual, but also, I mean, to show theorem in dimension 4. So there is this example, the knot. The knots are figures that exist in dimension 3, and usually the knot, by definition, it's an object which is complicated that you cannot remove it without breaking it. So the typical example is these two rings that one is taken into the other, and so you cannot break it, you cannot remove it without breaking it. Now, think that I have an extra dimension which is time. Then that figure does not exist anymore for a very stupid reason that one circle, in the direction of time, I will move it, and the other, it will stay at time 0. And then they will be in a different time, and so they will not meet anymore. So that's an example showing that you can, well, if you pass this obstacle of the vision, you can really go to higher dimension and say something.
Okay, since the time is almost up, we only have time for 2 more questions. Okay, there's one funny one. Let me go for that because they quoted Einstein. Albert Einstein said, imagination is more important than knowledge. But maths, like algebraic geometry, is too abstract. This is hard to imagine. Okay, there's one word I cannot read. I can see. So what's supposed to be fruit do you have to make you a great mathematician? What have you eaten to make you a... Okay, maybe apple.
What do you have?
Traits.
Do you have to make you a great mathematician? So I think I'm a good mathematician, but I'm not a great mathematician. I've known only a few great mathematicians, so I think you should ask them.
I am following you. Maybe it's not so important being great or not great. I think that if you are the mathematician that you want to be, some are very careful, some are more creative, and some like to prove a result with grid generality, some others prefer to find, maybe focus more and discover some funny things. I mean, the question is to, I think, being original, being yourself in some sense is very important. And also, I should say that with this emphasis on grid scientists, it's not very good in general. I wish it's something that I want always to insist on. That one scientist or two scientists is not science. We have a community, we form a community. And this community is essential because of the discussions, because of the seminars, because of the courses, and because also a scientist may be great at a certain time, and after a while he is not that great. He's simply an old person. So we need to transmit science, and we need to see arriving new people with a new mind, more original way of looking at things. So it's more important to think to science as, or at least maybe a specific field, even algebraic geometry, really as something which has some structure with many people having a role in that.
So can you say something to those first graduates in mathematics who want to pursue for a higher degree in mathematics? They want to be a graduate student, and do you have some advice for them?
Well, so I think that the advice was given by Professor Byte was really the best one, that you should do what really interests you, especially are young. If something interests you, then you can learn much faster, and just try to do that. And then, so I think that probably that's what unites us, all the Shaw Prize winners, that from a young age we did what we were interested in, what really drove us. And well, maybe I can speak for everyone. We probably did not follow the advice of our professors too much.
Maybe on a more personal viewpoint, I will add that life, or maybe professional life, it's not always interesting. I think we are very lucky as a scientist to have an interesting life, which started when we studied. So when you are students, you should really benefit. I mean, take profit of it in a maximal way. Maybe after a while you will renounce because it's hard to get a position, or because you do not get enough money. But then the danger is that sometimes you regret after that your life has become not as interesting as when you were a student. So I think that that period where on studies is really the beautiful one. Even for us, the period where we discover a field, it's really a marvelous period.
Thank you very much. Thank you both.
Thank you very much, professors. Please return to your seats on the floor. The last sections of the forum is on life science and medicine. It is our honor to have Professor Y.E. Chen to be our moderator. Professor Chen, please.
Well, so finally we moved from something which is billion or million light years away to something that we can only see with our eyes closed, to a subject or to an area that we can see, feel, and touch, and on Earth. So it is my pleasure to introduce the last session of today's forum, the Shaw Prize in Life Science and Medicine 2017. It's awarded to Professor Ian R. Gibbons and Professor Ronald D. Weil for their discovery of microtubule-associated molecular motors, proteins that power cellular and intracellular movements, essential to the growth, division, and survival of human cells. The two professors discovered two families of motor proteins dynein, and kinesin that move particles and membrane components along microtubules, promote the beating of microtubule within cilia, and move chromosomes back and forth as the hereditary materials prepare for the division of the nucleus during cell division. Human has more than 16 genes that encode different dyneins and kinesins that generate all the forms of the motilities mentioned earlier. And these motors are essential for all life forms, for all eukaryotic lives. Professor Gibbons isolated dynein from the microtubule structure, the exonym of cilia from the single-cell eukaryote, tetrahymena, and so that the enzyme activity of dynein, powered by ATP, which is the chemical energy source, is tightly coupled to the bending waves of enzymes. He subsequently cloned and sequenced the dynein gene and devoted his career to understanding how dynein works. And as a young scientist, Professor Weil discovered kinesin by studying the intracellular transport system of nerve cells. He developed single-molecule assays for kinesin and dynein that showed how these motors walk along a microtubule in a cell. He and colleagues subsequently determined the first crystal structure of kinesins and dynein. He also uncovered how ATP hydrolyzed led to structural changes in these motor proteins, which drive motion. So the motor proteins discovered by Professor Gibbons and Weil lie at the heart of key aspects of human biology. Without these motors, embryonic development, cell division, and the function of the nervous system and other organs would be impossible. Indeed, disease ranging from neuropathy, neurodegeneration, kidney disease, developmental disorders, and infertility have been linked to genes that encode these motor proteins. So the journey of discovery of these motor proteins must be very revealing and exciting. Unfortunately, Professor Gibbons cannot be with us today. So may I invite Professor Ronald Weil to come to the podium to share with us his journey of scientific discovery. Professor Weil, please.
Well, thank you very much. I need to start my slides here. I'd like to thank the Shaw Prize Foundation and the Hong Kong Science Museum for this invitation. And today I'd like to tell you about the cells, roadways, and motor system. They're also shown nicely here on this poster. Now this is something that I think all of the students can relate to this process a little bit because of understanding how we transport ourselves around in the city. So the way we move our goods around, whoops, not sure what happened there. Oh, I think I pressed it twice. The way we transport goods in a city, of course, is using cars, or trucks, which are carrying cargoes. And there's usually a motor hooked up to a trailer. But now if we peer into the life inside of a cell, we can see a similar type of system where there are also different kinds of cargoes that are shown in these objects here that I'll tell you more about. And if we look now at even higher magnification, we can see that these cargoes are traveling along roadways, which are called microtubules, and there are special proteins that serve as the engines, and these are called molecular motor proteins that are transporting these cargoes inside of cells. Now, this whole field of biological motility is in fact one of the oldest fields of study in all of biology. So even when the famous scientist Leeuwenhoek developed the first microscope, what he saw were amazing things happening in pond water, which I'm sure many students have seen as well. cells that are swimming back and forth. So he discovered this whole new world that was previously invisible to humans. And he described it as the motion of most of them in the water was so swift and so various, upwards and downwards and roundabout, that I admit that I could not but wonder at it. And in fact, even today, myself looking under a microscope and seeing this movement, I also experience this same wonder. Now, the first movement inside of cells was seen in the 18th century by Bonaventure Corti. And what he saw in a plant cell was that the chloroplasts are also moving inside of the cell. And he described it as, I know that the phenomena that I announce is too strange to be believed at first. I saw two torrents inside each section. One of the torrents rose on one side and descended on the other constantly. And this not once, but thousands of times, and for days and for entire weeks. I was saying, I wish we could write scientific papers like this today. But I think the way they wrote their scientific work, in fact, really captures the excitement that they felt, the excitement that all scientists feel when they discover something completely new. And for the students, also the reason to become a scientist is it's an amazing feeling to see or understand something that is completely new about the natural world. And that sense of discovery that Leeuwenhoek felt, I think, is what drives all scientists in the profession today. So I'll tell you a little bit about my journey to become a scientist, which maybe interests some of the students here. So I was born in a town not known for its science, but for other things, which was Hollywood. In fact, I felt very at home when I came to Hong Kong, because when I was walking around, I also found a street by the same name, so I felt like I was coming home here in Hong Kong. Now, my background was from a family that was not involved with science. In fact, my parents were involved in the entertainment industry. My father was a screenwriter, and my mother originally was an actress. So this was the environment of my house, although they both, even though they were in the entertainment industry, had a great admiration for science. In fact, my mom took me to a science museum when I was very young. And this was my elementary school, my graduation picture. And Professor White and Collard described that you should follow your passion in life. So my passion in life was to be a rock star. That's what I wanted to be. That's a picture of me. And the only problem with becoming a rock star was that, unfortunately, there was one person in my class that was better at it than I was. And that was Michael Jackson. So that was the end of my career. I taught him that moonwalk, but, he was much better at it than I was. So anyway, I decided, well, maybe I should find another passion. So my passion in high school took me to science, and I did a science fair project, and that was really a very life-changing experience for me, because I must admit I was not very interested in biology in school. I didn't think the textbooks were very exciting, but when I had a chance to do my own science fair project and be able to ask my own question that I wanted to find an answer to, I built a little laboratory in my basement. That was a really exciting experience where, I learned to use my curiosity to try to answer a new question. And that experience taught me that real science is a lot of fun, and that was kind of my path ever since. Now, a little bit later in life, this was now when I was a graduate student, working with my colleagues Mike Sheets, Tom Rees, and Bruce Schnapp. We went on a journey to try to understand this question, which is the transportation system inside of nerve cells. So let me tell you a little bit about why we picked nerve cells and why the transportation system in a nerve cell is so interesting. And that is that you're familiar that most cells are very small. You need a microscope to see them. And nerve cells are also very small, but they're extraordinarily long. So for example, one nerve cell in your body could have its quote-unquote cell body. The cell body is where the nucleus is and where the DNA is. That part of the cell is in your spinal cord. But that one cell extends a very long, thin process, and that process is called the axon. And this is kind of a long tube that conducts an electrical current. And in fact, that long, narrow process is what is found in a bundle of many nerve cells in your nerve bundle that travels down your leg. And then the distal part of that nerve cell is called the nerve terminal, and that part may excite your muscle, for example, to contract. So all of this belongs to one single cell. But the factory of where all the proteins of where that are needed for the cell are all made up in the cell body in the spinal cord. So those building blocks of proteins and membranes have to be shipped all the way from the spinal cord down to the end by your foot in order for that nerve cell to survive. The goods have to be delivered from the factory down to the end of the nerve. Now, just to put this on a scale that maybe is a little more intuitive for most people in the audience, instead of imagining a very small 10 micron or so size cell body, let's imagine a cell body in your spinal cord that's 1 meter in size. So that's about so big, 1 meter. And then the question is, where would that nerve terminal be if we had a 1 meter size cell body? And you can think about it yourself a little bit, but if that nerve cell body is 1 meter here, that nerve terminal would in fact be all the way in Shenzhen. That's the relative scale of how big things are. And the scale at which things are being transported, there's the little transport goodie, would be about the size of a marble traveling between here and Shenzhen. And it would take 2 days from this auditorium for that marble to travel to Shenzhen at the end. So in this transportation system, the way it works, just like our transportation system, is that you need a motor, which is the truck here, and that's carrying a trailer, which is carrying some consumer goods, and then this travels along roadways. Well, inside of the nerve cell, in fact, all cells of your body, there is a motor, and I'm going to come to the motor soon, but it carries, instead of a trailer, a container, which is a membrane vesicle. And this is essentially lipids that form a sphere that contains within it a variety of proteins and lipids and other building blocks. And they travel along a structure which is a biological polymer made up of a repeating pattern of proteins that's repeated end to end and forms a long cylindrical tube called a microtubule, and this acts as a roadway. So now let me tell you about the motors. So in life, there are 3 main types of biological motors that are used for force production and transport. And the first is called myosin. It was discovered actually and named originally in the 19th century. And it's called myosin. It travels along a track called actin. it's involved in all of your muscular contraction, it's involved in the beating of your heart, and so forth. Now, the other motor was discovered by my good friend and colleague Ian Gibbons, who shared the Shaw Prize in Life Sciences, and he discovered dining, as you've just heard, from cilia 100 years later after myosin. And the third type of motor is the one that I've been involved with, called Kinesin, which came from the squid giant axon, as I'll describe to you. So the reason why we decided to study this problem in the squid is that, first of all, most humans are not willing to donate their axon for obvious reasons. So we had to find not necessarily a willing organism, but at least an organism that we could dissect the axon from. But why, of all organisms, why choose the squid? Well, the reason is that the squid has a giant axon, and that giant axon is 100 times bigger in diameter than a human axon. And that makes it a very good system to dissect out of the squid and study. And these investigators, this is in the early 80s, Robert Allen, Scott Brady, and Ray Lassick, looked using a new kind of microscope called a video microscope at the inside of the squid. And you can see with the microscope all of these objects moving back and forth. So the inside of the squid axon is full of moving objects. These are mitochondria, if you know, these long squiggly things. And many of these small objects are these membrane vesicles that are traveling back and forth. Now, we wanted to find the motor that was involved in this activity. And here's the strategy that we use to do that. So imagine trying to understand how a car runs. Well, the car, if you just came up to it and you took it apart, has lots of different parts in it. And you know, the question is, many of these parts are not involved in movement. So, you know, for example, the seats are not involved in movement. Many of these components are not involved in movement per se. So if you can come up to the car and really figure out which of these parts are essential for getting the car to move and be able to put those parts back together again, then you could understand maybe about how the car works. So this was a similar type of goal, to take a very complicated system, which is the cell or the nerve cell, and which has many components. So it has actually many more components than this. There are maybe 20,000 different components in your cells or in a squid cell. And we wanted to take all those components out of the cell and then find out which were the essential parts in a test tube that we needed to put together to recreate motion. So that's what we did. And to give you an idea, this is actually what the natural system looks like a little bit in a test tube environment. You can see these tracks, and you can see these cargoes. That long snake-like thing is a mitochondria again. So these are the natural cargoes moving along these roadways. But we found out, fortunately, a trick that we could put in an artificial cargo, which is a very small manufactured plastic bead. And believe it or not, the biological motors got confused and attached to these small plastic beads, which you see here, and the biological motors would transport these small plastic beads just as though they were natural cargo. And I won't go through all the details, but this was a really key discovery because it gave us a tool to figure out what part of the cell was attaching to these beads and was responsible for the movement. And that work was done in this little town of Woods Hole during the winter where I did this work, and it was very good for doing work because there was nothing to do there in the summer except for work. Out of that winter came the discovery of a motor protein that I'll describe in a second called Kinesin. And many people ask me, how did you get the name Kinesin? Well, this is a good reason for all the students here to remember to call home and talk to your parents, which I'm sure your parents, if they're in the audience, will appreciate me saying. But I called my mother, and she talked to her Greek friend who knew that the word kine means motion in Greek, so we called it kinesin, based upon the Greek root for movement. So let me just tell you a little bit about these motors in comparison to motors that you're perhaps more familiar with. So the most remarkable thing is you've heard about the universe now at a big scale. Now we're going to have to delve into the microscopic realm because these motors are very small. They are 100 millionth the size of a meter, 100 millionth of a meter in size. So very, very small protein machine inside of your cell. Now, they also use fuel. So your car uses a chemical energy source. It uses a hydrocarbon. That hydrocarbon gets broken down, and the energy is used for movement. And in the cell, there's also a high-energy chemical molecule called adenosine triphosphate, or ATP. And that is the chemical fuel that is used by these motor proteins. Now, these motor proteins move at about 3 millimeters per hour. And that it is pretty slow, actually. It sounds pretty slow, certainly much slower than your car moving on a highway. But remember, these motors are very small. So if we think about the speed in terms of the size of these two motors themselves, we can see that the motors are actually moving 3 times faster than your car is moving on a highway. So they're very fast, and also, if we had motors moving all of the cars in the world, we probably would not have climate change because these biological motors are much more efficient in converting chemical energy into useful work. So now I'll just tell you a little bit about how we think that kinesin and dynein work. Now, the way we figured this out was, in some ways similar to the way scientists in the 19th century wanted to ask the question about how a horse gallops. And there was a big controversy about whether the horse had ever had any time when all of its feet were off the floor while galloping. And the way they solved that problem was to do a high-speed image of a horse, and they took different snapshots. And by understanding these different snapshots, they could understand the mechanics of how the horse could gallop. Now, I won't describe it in detail, but we could create snapshots of these very small motor proteins using techniques called X-ray crystallography and single molecule imaging. And we could create snapshots of how we think this machine works. And that is shown, this is not real here, but the shape here of kinesin is real. This is based upon real atomic information. And there are it's effectively a 2-engine machine of 2 identical parts here. And this is an animation of how we think this machine works. What you see flying in here is the chemical fuel, which is adenosine triphosphate, which gets hydrolyzed. And there are parts of this motor that change shape, particularly this yellow and red part here. You could see this red part here change its shape. And when it does that, it pulls the partner motor head from a rear sight to a forward sight. It's a little bit like a judo expert with a flip of the arm. The opponent goes from the back forward. And so this is how this machine works in a very organized hand-over-hand manner. Imagining like climbing up a rope, you put one hand and then the other. This is how this molecule crawls along the track, and the cargo would be somewhere way up here being carried along with it. Now dynein, which Ian Gibbons discovered, is in fact, a much more complicated biological machine. This shows the relative size of dynein and kinesin. You don't need to understand all the details. These are protein structures, but you can appreciate dynein is much bigger. And through work that Dr. Gibbons and our lab did together, we developed a model for dynein, again, from many snapshots. And again, there's a part of this machine here that changes its shape from yellow to red. And it has a long leg and a landing pad over here. And when this changes shape, it thrusts this landing pad forward and it can bind. Now, unlike the Kinesin, someone told me yesterday this looks like a movie from Bruce Lee called The Drunken Master, where he is moving in this complicated walking pattern. And this is a little bit how dynein walks. It doesn't undergo this very orderly action, but it kind of is moving in this more unidirectional, but still a little more random fashion along the microtubule. So I'll end here just by saying that the motor proteins that you've just seen here are really essential for all elements of life. I told you about a transport system that moves cargo from one place of a cell to another. But another kind of motility that probably all the high school students are familiar with is mitosis, which is how the DNA undergoes separation during cell division. And here is the DNA in green here. And these red structures are, in fact, the microtubule tracts. And the DNA aligns in the middle. And then the two equal parts of the DNA, which are called the sister chromatids, physically move apart from one another. And this beautiful choreographed dance of the DNA that happens every time a cell divides is driven by about 15 different kinds of kinesin and dynein to assemble this structure that's called the mitotic spindle and physically move the DNA apart. Also, even when you start off life, you start off with an egg and the sperm swim to meet the egg. The swimming of that sperm is driven by the dynein motor that Ian Gibbons discovered. In fact, he worked for many years studying a dynein in sperm. And then this fertilized egg has to divide into two, the first step of life. That first step of life, as I told you, is driven by these motor proteins. And then the embryo becomes more complicated and starts developing into tissues. Much of the organization of cells and tissues requires the organizing forces of these molecular motor proteins until you reach the final stage of complexity of being a complete newborn human being. But this whole process, this whole journey of life is also a journey of motion. It's a journey of these tracks and of these molecular machines. But in addition to the science, I also want to say that what is so wonderful about doing science is that it's about developing friendships and collaborations. Many people think of science as a very lonely thing where scientists work alone, and that is so far from the truth. Scientists work together in groups. Ian, this is a recent picture of Ian and I, have worked together for many years. We published a paper in 1989, and more recently, Ian moved to Berkeley. We began collaborating again. So one of the great privileges of this prize is I'm very happy to receive it, but I'm also particularly happy to be able to share it with my good friend, Ian Gibbons. And the other thing I want to say for all the students here is we present this great work and we're older scientists, but most of the work really in our laboratories is driven by young people, and it's driven by people that are a little bit older than you, but not much older. And this is my group right now of students and postdocs. And they are the people who are really doing all the experiments and who contributed over the years. All these young scientists are really the backbone of all the work that I've described to you today. So maybe this is similar to what you've heard, but if you're interested in science, these are the secret ingredients. It's curiosity, passion, and persistence. It's very interesting that some of the best students in school that get the highest grades do not end up being necessarily the best scientists. We've often seen students coming into UCSF that are not necessarily the top of their class, but have a secret combination that's very hard to define, but end up being outstanding scientists at the end. And the other thing is having fun, which you've heard. And I do want to just play this one video at the very end. But this video comes from a website that I've also been involved with called iBiology. And it's a project to film many leading scientists and put their lectures online. And you can look at it here at iBiology. It's also available on WeChat. And here is just some final
Are there any
remarks from
particular
Dr.
thoughts that you
Gibbons.
have, just looking back over this?
My general modus operandi, I think, has been to work with a technique for a while, and if it seems to be sticking, try climbing another side of the mountain, change your technique and start afresh and approach it in a completely different way. I mean, and I think that's useful. I've certainly found it interesting. I don't know how well it will work today, where there are many more people in science and most problems are more popular. Competition might make it difficult for you to do that, but certainly it worked very well for me. And so I would encourage anyone else to try doing it if they have the opportunity. But the main thing is to have fun, enjoy what you're doing, and then with any kind of decent luck, you'll get a great result.
Okay, great. Thank you very much.
For a very interesting talk. Looks from the video that all the kinesins move with the same speed. So my question is, what factors control the speed of these molecules?
So the question is, what controls the speed of the molecules? I didn't have time to go into it in this lecture, but these are enzymes. Probably the students have heard of enzymes. So it takes the chemical fuel, and then it breaks a bond in the ATP, and then it undergoes a step where it releases phosphate, and then it releases ADP. And this is a whole, and then it becomes empty, and then just like a carburetor, it can reload with the fuel, which is ATP. And there's a certain timing for that cycle. And which is, in the case of kinesin, about 30 milliseconds. And during one enzymatic cycle, where it's effectively taken the fuel, hydrolyzed it, and released it, it takes one step along the microtubule. So one of those steps where the head passes the other head, that corresponds to one hydrolysis of an ATP. So the speed is really determined by the step size, that's distance, which in this case is 8 nanometers, and which is the distance effectively between steps, kind of landing positions on the microtubule, times the cycle time. So it also turns out that there's not just one kinesin, but there are 45 motors of that family in the kinesin genome. And interestingly, the speeds of all of them are different. And they're largely determined by the timing of this enzymatic cycle. So some of them that build the mitotic spindle are very slow. In fact, they don't need to move very fast, but they need to be strong. And the ones that have to travel this very long distance in the axon are the fastest ones. So all of the motor properties have been tuned through evolution according to what these motors need to do in cells.
You talked about how different motor proteins move in different ways. So how do their different motions affect different functions?
Yeah, so that's a great question. I think the general answer is that there are numerous kinds of motion in biology that are very different. But I'll maybe give you one example, actually, of something that we don't understand, but related to your question. So the movement of the transport system along the track that I just showed you, in a way, that's a simple kind of motion. You just have to move in a very linear fashion along the track. And in the dynein family, there's only one type of dynein that executes that linear motion. Then I showed you this movement of the sperm, or the sperm has it has a sinusoidal wave, so it kind of beats, but it's a two-dimensional plane on which that beating happens, and that's how the swims by this two-dimensional wave. The cilia in your respiratory tract, if you take in all the pollution from Hong Kong, for example, you have to get rid of it, and there are cilia inside of your respiratory tract that's moving up particles all the time. Those cilia beat in a three-dimensional plane. I'm not sure, maybe I close my eyes and I can imagine one in 5 dimensions. Not working, okay. But it turns out that the motion of these appendages, these cilia, the cilia and the sperm, are driven by effectively between 10 and 14 different kinds of dyneins. And honestly do not know why there are so many dyneins that are contributing to this waveform motion. But the reason is that somehow, to generate this very oscillatory pattern, you probably need motors with different kinds of properties and different ways of regulating the motors so they can produce this complex beating pattern. So that's a great open frontier right now, I would say, in the motor protein field, is really to try to understand how do numerous kinds of motors cooperate to generate that kind of beating pattern that's much more complicated than just the linear transport that I showed you here.
Well, when the might is being transported there, let me just ask a question here. Is there any congestion in the transportation system of cargo in human?
Congestion. There is some thought that, particularly in some neurodegenerative diseases, even including Alzheimer's, that part of the problem, it's very hard to know what, in some of these neurodegenerative diseases, what is the original cause and what's the original problem, what's a later problem. But there is a body of work suggesting that in some of these diseases, there may be like a congestion problem also inside these long tubes, these axons, that is contributing to nerve death. So that's an area, that's an active area of research right now.
I think there's a question there. Over there.
Okay, so I have a question. How does Kinesin deficiency play a role and contribute to CMT diseases or muscular dystrophy? How does it play a role?
Yeah, so the question is, how do deficiencies or problems in kinesin give rise to certain diseases, largely? Yeah, so Yeah, there's a kind of disease, Charcot-Marie-Tooth disease, which is a genetic disease, and in humans, and scientists have then sequenced genes from these patients, and there are a number of different reasons why someone can get that kind of disease, but in many cases there are mutations in Kinesin motors that are found in those patients. And in those cases, the disease is probably not a complete failure of the motor. It's just a substitution of often one amino acid to another amino acid that makes the motor's performance not the same as the normal motor. And that's an example where that gives rise to a disease. And in those diseases like Marie-Charcot-Tooth, it's usually the longer neurons that die first. So the ones that are a meter long, that have the greatest need for that transport system, very small changes or problems with the transport system result in the death or degeneration of those neurons. In many cases, completely knocking out these motors would just absolutely be fatal, because I showed you in that at the very end that even just to make it to a successful birth requires that these motors are functioning well, even get to the stage of being a newborn. So many of the motor defects are rather subtle, like single amino acid changes. Another one example, not Kinesin, but maybe people have heard of young basketball players that suddenly die on the court playing basketball, and they discover they have an enlarged heart, and even though they're incredibly healthy, they have a mutation in the myosin motor that's causing the heart to contract. Again, it's a single amino acid change that gives rise to that disease.
There's a question over there.
So thank you for an inspiring talk. Recently, there's a drug that targets central duplication, and it showed promising results in clinical trials for cancer. So my question would be, apart from central, do you think, is there any other microtubule structures that we can target for cancer treatment? Thank you.
Yeah, that's a great question. Well, one of the very common drugs that people take right now for cancer is called Taxol, used very frequently in breast cancer. Taxol was originally found as a cancer treatment from the bark of a tree in northern, northwest United States, and they later found that the drug targets that microtubule tract that I showed you. So it doesn't affect the motor, but it's like kind of like bombing the roadways. And since I showed you that the microtubules are involved in the cell division and the DNA separation, that blocks the cancer cells from dividing normally. We, through a company, have tried to make drugs against Kinesin motors less successfully, and possibly the reason is that there are many, while there's one microtubule tract, there's about 15 different kinds of Kinesin motors that contribute to cell division. So the cancer cell may be rather smart, and if you knock out one motor, it still finds a way to survive working with other motors. But this company, which I disclose, I'm a founder of this company called Cytokinetics, has made drugs against, interesting drugs against, again, the motor in your heart, which is cardiac myosin. And it's an amazing drug that actually makes the performance of that motor better than the normal biological motor. So it actually enhances the performance of that motor. And that's being used right now in thousands of people around the world in clinical trials for patients that have heart failure. So some patients, their heart doesn't contract normally, doesn't pump blood well enough, and this drug actually makes the hearts of those patients contract more strongly. So that is a drug that directly works on the motor protein and modulates it. And I think it's a good example maybe for other diseases as well, that these motor proteins can be modulated by drugs, and we may be able to think of treatments even for neurodegenerative diseases that involve targeting the motors.
I got a mic, sorry. Thank you so much for a very elaborative and very interesting presentation, and congratulations on the Shaw Prize as well. And my question is, you showed us the video about, it's about the synthetic vesicle that you thought of, and then how the system actually took it upon, and then you eventually happened to find out. As I'm a research student, and then it's very important to think it in different aspects to come up with finding results is very important, right? So how did you have such ideas, and then making a synthetic vesicle, and how did you introduce it into the system and etc. and all these things? Can you, if you have time, you can tell us something about it?
Well, I can. I'll try to make it brief. But, a lot of times we present our results like we scientists are super smart. And the real truth is often something very different. So that experiment, in fact, was a complete accident. I describe it more in my iBiology talk that you can hear about it. But I'll try to make it a brief story, but it's a good story. So first of all, this whole axonal transport system, we were completely on the wrong track originally. So we thought the whole transport system worked with actin and myosin. That was our first idea. So we designed an experiment where we took myosin-coated beads, which we thought would move inside the axon. And that was the experiment we were going to do to prove it. Every time you do an experiment, you need to do something that's a control, which is something that, doesn't have like your test variable on it. So we had a control bead which didn't have any motors on it, and we got the exact opposite experimental result than, quote unquote, we wanted. The myosin beads didn't do anything, and the control beads that had nothing on them started to move. In reality, this is a longer story, but we should have picked up on that immediately, but it actually took us a while to really understand that result and then come to these brilliant experiments. So we made also a few mistakes on the path of getting there. But, in reality, this is so true of science that we are often limited by our imagination. We think, oh, we know actomyosin, so, maybe it is what we think it is. And it's very hard to imagine the unimaginable. And, of course, that is where we have to go as scientists. We have to go to the unimaginable. That's like always the frontier, and that's the dream of where you want to get. And sometimes we get there because we have a very clear idea, and sometimes it's more like accidental wandering that gets us in the right direction. And I think that's very important for students to know, because often you hear these scientists come up and they tell you about their brilliant experiments, and you go, oh my God, I could never be so brilliant. And if you really know the truth, that oftentimes, we scientists make lots of mistakes. And, hopefully you also learn from your mistakes and then you get on the right track. But, that's very much part of science too.
Okay, so last two questions, one is there, from there, yes. And then the other one is from here. Okay.
Thank you very much for your presentation. I've actually two questions for you. First,
you're only allowed one.
Really? Let me think about it. Okay. Okay, right. So the question is, like during asymmetric cell division in stem cell, the materials and organelles need to, distribute asymmetrically. So what is the mechanism like to control the dynamic of these kinesin or dynein to achieve this asymmetric distribution of materials?
Oh gosh, that's a very complicated question that has many, many answers. But like many things in biology, so first of all, most people probably don't even know what asymmetric cell division is, but in most cases, a cell divides equally in two, but there are some cases where the mother and so the daughters are equal. But in other cases, the mother is different than the daughter. And the mother and the daughter have different attributes. And there are some special cells in your body called stem cells where the mother retains its ability, its stem ability to keep dividing and giving rise to new daughters. But the daughters have new properties. But the answer to that is then you have to distribute molecules differently in the mother and the daughter, because the mother and the daughter have to be different. And a lot of that involves many motor proteins and complicated processes. Anytime you see something that looks non-random, and meaning it's even more non-random than the universe, it's like really dramatic differences in parts of the cell, that usually involves motor proteins actually physically moving molecules in different parts of the cell. And in some cases, even the spindle normally divides in half, but in asymmetric cell division, the spindle actually moves, so that when you divide in the middle of the spindle, there's a bigger mother and a smaller daughter, or the other way around. And there are often proteins that get transported by motors in one direction. And the other thing I didn't mention are RNAs. So RNAs are basically the basis of how proteins are made. In many cases, the RNAs themselves are also transported by motors. So you have mRNAs that are non-random in cells, again, transported by motors. So, but reality, I think we're at the tip of the iceberg of understanding that question of what makes a different mother and daughter, and what are all the things that the motor proteins are doing to make that difference. We know a little bit of it, but we don't know, I think there's a lot more for all the students here to learn. So I can close with that.
Okay, then let me just ask this question, because otherwise we run over time. So this is related. So is there any I just reformatted the question. Is there any specificity of the cargoes that dynein and kinesins carry?
Yeah, absolutely. So, you can imagine that, well, again, by my transport analogy, you have to hook up the right trailer, the right Federal Express cargo van to the right truck to get it moved in the right direction. And in that analogy, there is something like there's a trailer hitch at the back of the truck that hooks up onto the right cargo. Well, it turns out there's a whole other class of molecules, proteins, that are called adapters. And they are intermediates between the cargo and the motor. And the adapter is responsible for picking up the right motor and picking up the right cargo. And I'll just say one thing about this bead thing, also how we were so lucky. Most of those motors that are in reserve in the cell, they haven't attached to the cargo, they're inactive. So they're actually turned off, they're switched off. And so they're in reserve, but they're not burning ATP. And once this adapter protein hooks up to the cargo, it then hooks up to the motor, and it turns the motor on, so it becomes active when it's supposed to, and transports the cargo. So not with this bead experiment, we were incredibly lucky that it took all of these inactive motors, and when the motor bound to the surface of this plastic bead, it also switched it on to an on state. And if that wasn't the case, all of these motors would have been invisible. I probably would have never discovered Kinesin, and maybe I'd be a medical doctor or something. But anyway, so you know, there's just also some luck in biology too. But there's a whole fascinating other story, which is this regulation of motor proteins, which is true in how a cilia beats, like from what Ian Gibbons does. There's some motors that have to be on and off to create this sinusoidal pattern. And all of that transport in the cell also involves a very complicated system of finding the right cargo and regulating these motor proteins and turning them on and off at the right time.
Well, so let us thank Professor Weil for an inspiring talk.
Thank you very much, Professor Weil and Professor Chan. Please return to your seats on the floor. Thank you, professors, for sharing your experience in doing science. Mr. Shaw Norris 2017, The Challenges and the Joy of Doing Science Forum is now concluded. We are deeply appreciative for the professors joining this event, sharing their experience in their work with us, and giving their insights into the young one's mind on science. Thank you.